Now that we've taken the time to define simple harmonic motion and talk about its defining characteristics, it's now a good idea to start investigating some systems that actually do exhibit simple harmonic motion. And we're going to start off by looking at these systems that involve masses oscillating on springs, which we're simply going to call mass spring systems. Now, a mass spring system can be set up in a couple of different ways. It can be set up horizontally, so we've got the mass resting on some surface. We're going to assume this surface is frictionless to keep our life a little easier. It's going to be attached to a spring that's attached to something anchoring that spring in place. Or we could have it in a vertical setup like this, where the spring is attached to the block and the spring is hanging from the ceiling. Now, real quick note. In this particular spot right here, we're going to say that the forces on the objects are balanced. So these are their equilibrium points. And let's go ahead and say we displace them from their equilibrium points. So we're going to pull the block on the left to the right. We're going to pull the vertical block down. And when we let go, these are going to start oscillating back and forth. So they're going to go back to their equilibrium positions, past their equilibrium positions, then they're going to reverse direction and go back to their original positions, and once again reverse direction again. And we're going to go ahead and stop it right there. Now, we would say that this would keep oscillating in this particular pattern until we had some more than likely energy loss from things like energy in the spring, but we're going to ignore that for now. So we're going to assume that these patterns are basically repeating indefinitely until we go ahead and stop them. So while doing that, let's look at some basic terminology we have with both of these systems, which is, first off, the equilibrium position is mark them X naught here. For both of them, that's where the objects basically sit naturally. And the distance that we pull the horizontal system to the right or left, or the distance that the vertical system is pulled up and down, and that it then oscillates between these 2 points, is a distance known as the amplitude, which we abbreviate with a capital A. And we're going to go and say these masses have some mass m, and that these springs have a spring constant k. And we're going to go and say that the springs are massless, and by that we just mean that the blocks attached to them have way more mass than the springs themselves, so we don't have to worry about any sort of weird acceleration with the springs. Alright, but let's go ahead and take the time to also look at the forces on this system. So when they're at equilibrium, these forces are balanced. So on the horizontal system, we're going to have a normal force and a gravitational force balanced. On the vertical system, we actually have the spring force and the gravitational force balanced. But now when we start displacing these back and forth, well, we're going to start having a restoring force. So in the horizontal situation, that restoring force is going to be proportional to the displacement and opposite direction of that displacement, and that is going to be the spring force. If we pull the block to the right, it's going to have a spring force to the left. If we push it to the left, so we compress the spring's going to push back to the right. So this right here is that restoring force. But for the vertical system, this is slightly more complicated, because as we see, we already have a spring force. So instead, what's really oscillating is this combination of the spring force and the gravitational force. Because at the very, very top, that's actually when the spring force is going to disappear completely, and we're just going to have gravity down. And at the bottom, we're going to have gravity down and then some spring force going up. That's going to be bigger than it was in equilibrium. So that net force is in fact the restoring force in this situation. We're going to pretty much really focus almost exclusively on horizontal systems though, partially because they are so much easier to analyze. Now, what factors affect the period of these oscillations? Because remember, this is simple harmonic motion, which means it is periodic. It's repeating and oscillating at this constant rate. And we're going to abbreviate this period T sub S, where that S really just stands for the spring and like mass spring system. Well, if we increase the mass on the spring, we would expect the period to go up, because we have more mass. It's going to have more inertia. It's going to be hard to stop the mass and to speed it back up once it's stopped. So with that inertia, we'd expect the period to go up. So those are going to be directly proportional. Now, if we move the block more to the right or left or up and down, we're going to increase that displacement, so it's going to have to cover more distance. And so we would expect the period to once again go up. It's going to go in slower oscillations. But if we have the restoring force increased, if we increase that restoring force, that's going to really accelerate it back to that equilibrium position faster, and we would expect the period to in fact go down. So we get something that looks like this over on the right. Now, I'm going to go ahead and tell you, I'm not going to derive this equation perfectly. We could do it, but it would just take a lot of extra time. And additionally, we would have to start going through some other equations. I don't necessarily think it's worth the effort this time. So please trust me that this is in fact not just magic, it does come from somewhere. But really, the period of this mass spring system is going to be equal to 2 pi, the square root of these factors. However, we can simplify these factors a little bit because we can remember, oh, well, the restoring force for the horizontal system is a spring force, and honestly, even for the vertical system, even though it's not exactly the spring force, it's going up and down with the spring force, so it follows a similar pattern. And what would happen is, well, we look at this and our displacements cancel, and we're actually left with this equation here, that the period of a mass spring system is actually just 2 pi, the square root of m over k, where ts is the period in seconds, m is the mass on the end of the spring, we're not worried about the spring, in kilograms, and k is the spring constant, or stiffness, of the spring in newtons per meter. And that makes sense, because if we increase that stiffness, it's going to pull back more, it's going to cause the system to oscillate faster. If we decrease that stiffness, if it's not as tightly wound, it's not going to pull back as much, and the system's going to take slower to complete its oscillation. So really, there's only this factor mass and this factor spring constant that affect it. And this is true for both horizontal mass spring systems and vertical mass spring systems. And one important point I want to bring up, though, is this means that the amplitude of the system really has no effect on the period. If I pull it further away from equilibrium, it's still going to wave back and forth in the same time period, because even though it's been displaced more, the force is going to pull it back even more, and that's going to make up for that. So let's start to look at this in just a little bit more detail so we can derive a few more interesting points. So let's say we have a horizontal mass spring system here on a frictionless surface, and let's say we've gone ahead and displaced this block a distance, its amplitude, a, from its equilibrium point x naught. Let's say that time t equals 0 is the moment we release it. So as soon as it's released, it's going to start waving back and forth. It's going to return to equilibrium at some later time. It's going to go past equilibrium all the way to the amplitude point, go back to equilibrium, and go back out. So this, as we look downward, these are basically like individual snapshots of the system as the block is waving back and forth in time. So time is going forward as we look down this series of pictures. So let's go ahead and describe a few things we know. Well, first off, with regards to position, the position over here is to the right, 0 to the left, 0 to the right. If we define the equilibrium position as 0, then that's pretty easy to identify. But what about the velocities? Well, for the velocities are going to be 0 or practically 0 at these amplitude points. So at this first position, the middle position at the end, because that's when the block is changing direction. So it's going to have to rest for just an instant and start to speed up the other way. Now you will notice that the velocity on this first one is 0. That's because we're going to say this is so close to the moment it's released that it's barely had any time to pick up speed. But if we look at the other two positions, when it's at equilibrium, that's when the velocity is at a maximum. And when it is moving to the left, as we see here, the velocity is to the left. When it's moving to the right, the velocity is to the right. But now let's talk about the net force direction, and keeping in mind that whatever direction the net force is, that's also the direction of the acceleration of the system. And remembering that for this particular system, that net force is just the spring force. Well, if that's the case, when it's at equilibrium, we're going to have 0 spring force, because that is when basically the string is not stretched or compressed. When we pull the block to the right, the spring force is going to pull it back to the left, so that's at the top and the bottom. And when we push it to the left, it's going to be pushing back to the right. Now, a lot of people get freaked out by this because they go, well, wait a second, how is this net force and acceleration 0? Because it's moving at this equilibrium point. And that's true, but keep in mind it was moving already, it was already accelerating before this point, and so when it gets to equilibrium, its momentum basically carries it through, even though that net force and that acceleration goes to 0 for at least a moment. Now, what about the energy of this mass spring system? Well, we can go ahead and look at this and recognize that the only types of mechanical energy we're going to have at any of these points is kinetic, if the block is moving, or elastic potential energy, otherwise known as spring energy, if the string is stretched or compressed. We're not going to have any gravitational potential energy, or if we do, it will be the same for all of these, because this is a horizontal system, so it's going to be pretty consistent here. If this was a vertical system, we would also have to consider UG, but we're really going to be focusing more on the horizontal just for right now. So if I look at this, let's look at the very first situation. Well, at that moment, the velocity is practically 0. It's barely done any movement yet, and the string is very stretched. This is going to be primarily, in fact, all elastic potential energy. But when we get to the equilibrium position, well, now it's moving. some velocity, so it has kinetic energy, but the string is no longer stretched or compressed, so in fact now it is all kinetic energy. When it goes past equilibrium to this minus amplitude point, well, the string is really compressed, it doesn't move for an instant, so all elastic potential energy. When we come back to equilibrium, all kinetic, and when we go to the final point, back to the original position, all elastic potential. And so what we notice is that the total energy of this system is in fact conserved, because we have no net external forces on this system. There's no friction, and even though gravity and a normal force would be external, they are balanced, and that spring force, that is internal to the system. So we should have mechanical energy conserved in all these situations. This should always be equal to some total E, and that makes solving a lot of problems very, very simple. Now keep in mind, if instead I was looking at some position like here between two of these, between an amplitude and an equilibrium, we would have some combination of elastic potential and kinetic rather than just one or the other. But taking this one step further, keep in mind that at all the points where we have all kinetic energy, well, that means the total mechanical energy will just be equal to the equation for kinetic energy, or 1/2 mv squared. And at all the points when all the energy is just elastic potential energy, well, that equation is 1/2 k delta x squared. But at these points, that delta x is the amplitude, so we can rewrite that as 1/2 k a squared, and that's going to in fact be the case at every point it is at an amplitude, or in other words, a minimum or maximum position. So let's look at a brief example. Let's say we have a block of mass 0.5 kilograms oscillating on a frictionless surface while attached to a spring that's anchored onto something, and the spring has a spring constant of K is equal to 50 newtons per meter. The amplitude of the block's motion is 0.8 meters or 80 centimeters, and we want to calculate the period of the block's motion and the velocity of the block when it's at that equilibrium position. Now, if you feel confident with this, feel free to go ahead and pause, try it on your own, and come back and see how you do. But I'm going to go ahead and move forward at this point. So if I want to calculate the period, well, that's going to be pretty straightforward. I'm just going to use this period equation of Ts is equal to 2 pi the square root of m over k. I have the mass, I have the spring constant, so I can just substitute those values in, stick this into my calculator. I definitely can't do this in my head, and I would get a time, or a period, of about 0.63 seconds. It's going to take that long for the object to return back to whatever its initial point was. Now going a step further, okay, let's say we want to calculate the velocity of the block at equilibrium. Well, let's keep in mind that the energy of this system is conserved. So if we look at the energy of the system at equilibrium, this has to equal the energy of the system when it's at some amplitude A, for instance, when it's at its maximum or min value. Well, at equilibrium, all the energy is kinetic. When it's at this amplitude, all the energy is elastic potential. So these two values are going to be equal to each other. And I'm going to go ahead and sub in the equation. So I have 1/2 mv squared is equal to 1/2 k a squared. I went ahead and put in a rather than delta x because we're at the amplitude position. And I'm going to go ahead and cancel out those 1/2s, and I'm going to solve for v. So I'm going to basically divide both sides by m, and I'm going to take the square root. So I've got k, I've got a, I've got m. I just stick in my numbers now. And if I stick that in my calculator, I get that at equilibrium, the block will be moving at 8 meters per second. And in fact, that will be its maximum velocity, because that's the point where it has the maximum kinetic energy. Alright, so that concludes our lesson on mass spring systems, and what are the main takeaways? Well, can we analyze the velocities, accelerations, and forces involved in a mass spring system, particularly for that horizontal setup? Can we calculate the period of such a system using T sub s is equal to 2 pi the square root of m over k? And can we analyze the energies of a mass spring system and use that conservation of energy to determine the specifics of its motion, keeping in mind when it's at equilibrium, all the energy is kinetic, and when it's at its amplitude points, all of that energy is in fact elastic potential energy.